Okay, so today I am willing to answer some questions on 6.4 if you have any left to ask, and I would also be willing to answer some questions on 6.5 if that would be helpful. So does anyone have any questions that you'd like me to start with? Yes, sir.
There are some questions on 6.5 that it says you need like a calculator for.
Okay.
Would you be using like the integral function calculator to calculate it if we can't like figure it out, or is there always a way to do it in the book?
You shouldn't ever need an integral function in your calculator in order to do one of these. I think all you would really need is kind of like some sort of pretty much just your basic calculator. What problem in particular are you thinking? Kind of like in the
problems 22, 23, and 27 were not ones I could figure out.
Okay.
So if you look at one of them,
Yep.
help me out.
I had that same
okay.
thing with those three questions.
Yeah, let's take a look. So let's start with, you said 22 was one of them?
Yeah, 6.5, 22.
Yeah, 22. So this is section 6.5, number 22. All right, so we have y equals sine x is our function for 0 is less than or equal to x is less than or equal to pi, and we are wanting to compute. So write and simplify the integral that gives the arc length of the following curves on a given interval, and then try to approximate what that integral actually is. Okay, sounds good. So first of all, we have our arc length formula, right? Which is a little bit different than what we've been working with, but it's pretty straightforward. So our length is going to be equal to integral. We're going from an x value to an x value, 0 to pi. And then what goes in here?
Square root of 1 plus
Square root
y times
1 plus, and this is the part where it's easy to mess it up if you're not careful, is you want to take the derivative of this and put it in here and square it. It's easy if you're hurrying to just put this in here and square it, and that's not as good. So what's the derivative of sine of x? Yeah, so cosine of x, and then we want to square that, so cosine squared of x, and then that's dx. Correct? Yeah, so the question is now, okay, now that we've done this, what do we do? Yeah, and this is, this is definitely a little bit more tricky to figure out what is this guy. There's no nice trick here to get, it would, this kind of reminds you of sine squared x plus cosine squared of x equals 1, but it's not quite right, correct? So it's very close. Any other tricks that we could try? Maybe. I don't know how helpful they would be. So I think that at this point, this is the correct integral, but I think to actually evaluate this integral, we're probably going to have to use a calculator in some way. So one way you could do it is kind of to graph it and use some sort of an area function. So actually graph this thing, the square root of 1 plus cosine squared of x, and then use some sort of a tracing thing on your graphing calculator to see how much area approximately is under that curve between 0 and pi. There's no nice antiderivative that I know of for 1 plus cosine squared of x, especially square rooted. So there's nothing nice here to work with, unfortunately. Yeah, 1 second. Yeah, no, it's just no good. So, yeah, that's going to be your best bet. Is just to graph that thing. Look at the curve between 0 and pi. And then sometimes the graphing function has something where you can compute area, approximate area under that curve. If you wanted to use an integral function and actually type that in and see what it gives you, that's fine too. So, but we can't take the antiderivative, unfortunately.
So there's no U substitution?
There's nothing nice. No, not at least not with what we know right now.
Oh, okay.
There's nothing that can be done right here. And honestly, even with what I know right now, nothing is like jumping out at me as really, really great. Because there's no U substitution you can make really, because there's nothing outside the integral to become the du. And so, yeah, you could sort of approximate it. It's not great. It's pretty bad. Yeah.
Okay.
So just use your calculator and some way of determining an approximate area under that curve. Oh, yeah. It's a length. Yeah, but to find that length, you have to find the area under that curve. Does that make sense? So so what we're doing is the length in general, right, is integral from a to b of the square root of 1 plus f prime of x dx. Squared, thank you. Squared, correct. So what it's really saying is the way that you find the length of the curve f of x from a to b is find the area under this curve. So the length of the f curve is the area of the square root of 1 plus f prime of x squared curve. Does that make sense? So it's kind of like this curve, the area under this curve, gives you the length of the curve f of x. Okay. So what I'm saying when I say take the area under the curve, not the original curve sine of x. I don't care what the area under sine of x is. I want to know what the length of sine of x is. But the length of sine of x is the area under this nasty curve. Does that make sense?
Yeah.
Okay. Other questions? Yes.
On 6.417.
6.417.
I set it up, but I didn't really know how to integrate it.
Okay. 17. So this is 6.4, number 17. We've got y equals cosine of x squared. Y equals cosine x squared. We have y equals 0. We have for x between 0 and square root, oh man, no, pi over 2, about the y-axis. All right, so let's just draw this real quick. We've got the curve cosine of x squared, which still is going to basically at 0, cosine of 0 is still 1. So it starts up here. And then it starts going down, but it might go down at a little quicker pace. Where does it hit 0? Well, you'd have to square something and get pi over 2. So square root of pi over 2 is perfect. So it's square root of pi over 2. This hits 0. So it kind of goes down like this. And then y equals 0, of course, is the x-axis. And we say between x equals 0 and x equals square root pi over 2. So we're talking about this guy. Okay, so they say take that shape and revolve it around the y-axis. So when I do, I get something like this. All right, so now is a great time to say, okay, do we want to use the disk method? Because already I see, look at that cross section, that's a nice disk. Or do I want to use the shell method? And at first glance, I might say, hey, this looks like a really good disk method problem. Until I say, okay, so what do I need? What axis gets cut if I make disks? The y-axis, so that means I need to solve this thing for x. And as soon as I see that, I say, I don't really want to do that very bad, right? I don't want to solve this for x, because it's going to have an inverse cosine and then the square root of an inverse cosine. That sounds really bad. So what if I just kept it as is? That seems better to me. And so in that case, if I want to leave it as is, I want to cut this direction. And if I cut that direction and spin, then I'm getting a shell. Okay, so I want to use the shell method. And if I use the shell method, I'm cutting the x-axis, so I want x stuff inside of my integral. Okay, so let's see, maybe I'll move over here. So the volume is going to be equal to the integral from 0 to square root of pi over 2 of, we're using a shell method, so we have 2 pi RH. So 2 pi r, in this case, if this is an x value right here, then the radius is just x. So 2 pi x, and then the height is just the function itself. And the function is cosine of x squared. So this is times cosine of x squared dx. And this is a perfect time for a u substitution. We could u substitute for the x squared. So let's let u be x squared. Du then would be 2x dx, and I have a 2x dx here. So the only thing left over is the pi. I could pull that outside the integral, and I'd have pi times the integral of cosine of u, and then 2x dx all becomes du. And now I could change my limits of integration just so I don't have to go back to x again. If x is 0, u is 0. And if x is the square root of pi over 2 and I square it, I get pi over 2. And now we have that integral to compute. So antiderivative of cosine of u is what? Sine of u, right? So it's sine of u evaluated from 0 to pi over 2. 0, pi over 2, which is, we have pi, and then we plug in the pi over 2. Sine of pi over 2 is what? 1 minus sine of 0 is 0. And we just are left with pi. Sound good?
I definitely took that as cosine squared of x, so then I was running into problems, but that makes
Yes.
a lot more sense.
Yes. Very good. Other questions? Yes, sir.
Can you just briefly go over what a Riemann sum is? You mentioned it in your lecture for 6.5, I believe, when you were like proving that
Yes.
the surface is there.
Yeah, so when I was proving like arc length?
Yeah.
Yeah, sure. So what is a Riemann sum? Yeah. For like a very good explanation, you could go back and watch the lecture on it. But if
I think you mentioned it, but you didn't really explain what a Riemann sum was. So I was just wondering what you have to say about it.
yeah. So what a Riemann sum actually is it's kind of like the definition of a definite integral has something more to do with like cutting up rectangles, right? And it's kind of like a true Riemann sum looks like the limit of a sum of some function at some, let's say x sub k star times delta x sub k, where k is going from 1 to n typically, and this is the limit as n goes to infinity. Now, this may not be super helpful. This is something that you talk about in Calculus 1. So basically what a Riemann sum is if you think of this as a width and you think of this as a height, then you're on the right track. You don't have to think of it that way. It isn't always that you're cutting up rectangles. In fact, most of the time in this course so far, we haven't been cutting up rectangles. We've been cutting up something like a bunch of disks. So when you cut up a bunch of disks, then this function in here isn't a height anymore. It's the area of a disk times a small change in x, which is the width of that disk. And when you sum over the width of a bunch of disks, basically what you're saying is, like, let's say I have a football and I start cutting it up into disks, and then each of those disks has a little bit of width. So if I wanted the total volume, I could take that little tiny width, multiply it by the area of each individual disk, and that would give me some sort of a volume. Add all those volumes together, and I'd have an approximation for the volume of the football. And if I let the number of cuts go to infinity, then I get the actual. Does that make sense? So a Riemann sum is just saying, cut it up into a lot of pieces, and then add up all the pieces, and then let the number of pieces go to infinity. And that's basically what a Riemann sum is. Yeah. Other questions? Yes.
Going back to number 22 from 6.5.
Uh-huh.
So I plugged it into like a calculator, and then so it gives you like the antiderivative, and then do you do like from 0 to pi, or like of the antiderivative, and then
Right. So it gave you an antiderivative. Do you have like a TI-89 or something, or you plugged it into?
I put it like
Okay. What did it say?
it says sine of 2 pi plus, or no, not pi. Sine of 2x plus 6x over 4 plus c. I know the c is
Sine of 2x plus 6x
over
over 4. Uh-huh. Okay. And then, so this is what they're saying is the antiderivative, correct?
Yeah.
Yeah. And then you would want to evaluate that from, was it 0 to pi? Yeah.
4. Okay.
Yeah.
I just wanted to make sure that was the correct direction.
Yeah, that's, I'm trying to think how do they do it?
It shows you the steps.
We'll actually do it in just like a couple more weeks. What they're doing is they're using something called a trigonometric substitution. And so we'll do it very soon, but we're not quite there yet. But it could be done with a trig sum. Yeah. So I will show you very soon maybe a little bit more than we want to do right now, though. Yes, sir.
Can we do 65 on 6-4?
6-4, number 65. Sure. Okay. Use the shell method to find the volume of the following solvents. Yeah, sure. Okay. So this is 6.4, number 65, correct?
Yes.
Okay, so we want a right circular cone. Of radius 3 and height 8. Okay, so use the shell method to find the volume of that. Okay. So it really depends on how you decide to draw that cone. And it doesn't matter which way you draw it, just as long as you understand what you drew. I think the easiest way to draw this, and remember, we want to create a cone by spinning something, right? We want to spin something around the axis and then get the cone that we wanted. So this is the way that I'm going to do it. It's not the only way. So if I went out here to 8, and then I went up 3, and then I connected those dots, and then I said, this is my region. Let's spin that region around the x-axis. Then what would come out would be correct. It would be a cone. Its height would be 8, and the radius would be 3. Okay, yeah, this is perfect. And so if I could just say, okay, so what's the volume of the shape generated by that triangle? Then I'm good to go. To do that, I guess I need to know what's the equation of that line. Let's see, it would be y equals, I need mx plus b. So the slope of this thing is down 3, 1, 2, 3 over 8. So negative 3 over 8 x plus the y-intercept, which is 3. Let's see if we buy that. If I plug in 0 for x, what should I get? 3, and I do. If I plugged in 8 for x, what should I get? 0, and I plug in 8 and I divide by 8, I get minus 3 plus 3, which is 0. So everything's fine. This is correct. And then I want to use the shell method. So if I use the shell method, maybe I didn't set it up very well. That's okay. But then I'd want to cut it this way and spin. Correct? That's how I get my shells. If I cut this way, then what axis gets cut? Y. So that means I need to put in like a y function, not an x function. So I need to solve that equation that I just wrote for x. So if I solve this thing for x, I suppose I get y minus 3 is equal to negative 3/8 x. So I'd have to multiply both sides of the equation by negative 3/8. And so, no, I'm sorry, negative 8/3. So if I multiply both sides of the equation by negative 8/3, I get minus 8/3 y. And then minus 8/3 times this guy's going to be positive. The 3's will cancel, and I'll just get 8 equals x. Does everybody feel good about this? So let's see, if y is 0, I should get 8. And if y is 3, I should get 0. Perfect. Okay, so this is my equation in terms of y. And I want to find the volume of that cone, which is an integral from a y value to a y value, so 0 to 3, of 2 pi r, if I'm sitting at this random y, the radius is y, h is the function. And in this case, the function is negative 8/3 y plus 8. So this is minus 8/3 y plus 8 dy. Okay, let's multiply that out. So the 2 and the pi, I suppose, can just come out completely. I get 2 pi times the integral from 0 to 3 of, if I multiply through by y, I get minus 8/3 y squared plus 8y dy. Now I could take the antiderivative, and I get 2 pi. Antiderivative here, I'll bump up the power by 1 and divide by the new power, and I'll get minus 8/9 y cubed plus, do the same thing here, y goes to 2, divide by 2, and I get 4y squared, evaluated from 0 to 3. Let's plug it in. We get 2 pi times, plug in the 3. 3 cubed is what? Yeah, 27 divided by 9 is 3 times 8, 24. So negative 24. Negative 24. And then 3 cubed is 9 times 4 is 36. Minus, and then plug in 0, and I get 0 and 0. Okay, 36 minus 24 is 12, times 2 is 24 pi. And that's it. By the way, what is the equation, like, officially from geometry of a cone? Does anybody remember?
Is it 2 pi squared h?
I don't think that's quite right. It's probably in your book, too.
Doesn't it have 3/8 in it?
3/8? I'm not sure if it does. Probably right at the beginning. Anybody?
Pi RH over 3.
What did you say?
Pi RH over 3.
That might be right. It's, for whatever reason in my mind, I'm thinking of 4/3, but I'm gonna check it real quick.
1/3 pi.
1/3 pi r.
4/3 is a sphere.
What's that? Oh, boo. I should remember myself. I'm feeling guilty, but I don't want to say it wrong.
It's 1/3 pi r squared h.
Yeah, here we go. 1/3 pi r squared h. Yeah. Okay. I was debating between 1/3 and 4/3. 1/3 pi r squared h. Okay. So this is my volume formula, and it would be kind of nice to see, does it work based on what I just got? So if I plug in 3 for r and 8 for h, then 3 squared is 9, divided by 3 is 3, times 8 is 24 pi, right? Yeah, we're good to go. So it does work. So we know we got the right answer. So it's also kind of cool, how do you figure out, like, that's one of the really cool things. I love these problems, by the way. because these are the types of problems where it's like, okay, how did you even come up with the formulas for like the volume of a cone or something like that? Have you ever thought about that? It's like, how do you come up with the formula for the volume of a sphere? A sphere's curvy, right? So how would you come up with the volume? But then now that you know this, it's kind of like, oh, if you took like a semicircle function, spun it, that would create a, that would create a sphere. And if you add up all those cuts, you would get the volume. So we could compute like the volume of a sphere fairly easily just using like a semicircle and spinning it and using either the disk or shell method, whichever one we wanted. So that's pretty cool. Other questions? Let me see if anybody has written anything here. Oh, yeah. Somebody wrote in the equation for a cone. I did not look. That's good. Okay, if there are no more questions, I'm not going to keep you. You make sure that you've watched everything you need to on 4.5 on the arc length by Monday for sure. We'll take more questions on Monday about 6.5. Other than that, have a good weekend, and I will see you on Monday.